Okay, so here we are for week 5. Last week, I decided to cut the lecture short. I decided there was too much information in it. Your TAs, some of them had said that they thought it was too much, and when I got into the recording of it, I agreed. So, having heard their feedback and seeing where we were, I decided to make the same choice. Last year, they did both of these lectures as 1 week, and everybody did great. In fact, I usually get a little bit in trouble that my marks are too high. That said, I think it's not a bad idea that we have this set up to be over 2 weeks. I think I'm going to go forward with that from now on. So today, we're going to continue with the concept we talked about last week. Last week, we talked about the fact that an object that is in equilibrium, any part of it is in equilibrium. So if we have gone to the trouble of proving that it's in equilibrium, we know that any part of it must be in equilibrium. Equilibrium doesn't mean deflection. Equilibrium is saying that it is not flying off into space or spinning about in space. Small internal movements are something different. That is mechanics of materials. We're not talking about that. We're talking about the object as a whole, that it's not going up and down, in and out of the page, back and forth, or then spinning about all of those axes. And so last week, we looked at an object that we found what reactions would it take for that object to be in equilibrium. So we knew what the loads were on it, and then we figured out what it would take for that to be in equilibrium. Once we knew it was in equilibrium, we knew any part of it must be in equilibrium. So if we said, you know what, let's ignore this half of the object and pretend it's not there. We know it's there because it's holding this in place. When we looked at the object as a whole, we used 3 equations to figure out what the reactions were that kept the object in equilibrium. Well, our small part of the object now, we know that there's a reaction, possibly a load on it, that is acting on it, but we know it can't be moving in space. So there must be something happening internally that is holding that thing still. We don't know what those forces are. So we say we know there must be something there, and we have the opportunity to figure it out. Let's make some placeholders for what these unknown forces are and use our same 3 equations to solve for those internal forces. And so that is, what is the sum of the forces in the y, what is the sum of the forces in the x, and what is the sum of the forces about the z axis. So remember, we can use our right-hand rule to talk about that. And we want the sum of all of those equations to be 0 because our object is in equilibrium. So that's what we talked about last week. So we want things to stay still. If they stay still, they're in equilibrium. If they are in equilibrium, they aren't moving in any of the 6 degrees of freedom. We often break the problem into a 2D problem that only has 3 degrees of freedom, which means we want the sum of the forces in the x, the sum of the forces in the y, and the sum of the moments about the z-axes to be 0. We can then use those equations to solve for the reactions of the system that keep it in static equilibrium. We can cut sections of that truss to determine what internal axial forces must keep them in place. And we started to talk about this last week, and I showed you a slide, and we're going to show that slide again this week. What happens if that object isn't a truss, but is a beam? So what happens then? So let's talk about that. Let's remember what bending is. Bending is a force that acts to bend a component, putting one side of the part in tension and the opposite side in compression. It's the same as tension and compression couples. So it kind of looks like this. We have these 2 acting in equal and opposite directions, and these 2 acting in equal and opposite directions, but these 2 at the top are pushing together, which we know for internal forces means compression. And at the bottom, we have these 2 arrows pointing away, which we know for internal forces means tension. So last week, we solved for some trusses, and we found that if we had loads pushing downward on an object, it would bend like this. And we used method of sections to find out what the internal axial components were. Now, we know that if something's bending like this, the top chord's in compression and the bottom is in tension. But then we also saw that there was another internal force in this web and in the struts. So these elements along here also had axial loads. But if this is a beam, we don't have these objects in here to deal with that load. So let's talk about this internal web load right here. If we were cutting this object right here, we know, and we did this last week, that we could break this internal axial web element into its X and Y components. So we could make it look like that. So I'm just redrawing this a little bit. We know that whether we cut it here or whether we cut it just this side of this strut element, so right here, it's the same thing. So essentially we can shift this point almost right down to here. So really then, this is in the same plane as this. So we can add them linearly. So we can just rewrite it like that. Well, we know that if we have a force going in that direction and a force going in that direction that are equal and opposite, we have a couple. So we know that we can rewrite this as a moment. So let's just pretend that this wasn't the truss, but just a big object. So the same thing, we've got our compression in the top and our tension in the bottom. That part of it is the tension in the bottom and part of it is the internal force in that web. And we're still left with this weird Y element, but we know this top and bottom force can be rewritten as a couple, or we can rewrite it as a moment, that those are a force couple, and we can rewrite that as a moment. Well, look at this. Moment. And do you guys remember in the first 2 weeks I talked about this force shear that is like two planes slipping past each other? Well, look, I am saying that there was a big beam here that I've cut on this plane. Well, what we're talking about with this unknown internal force is what is that internal shear? What is happening at that plane? We know it's not slipping past each other, but there's loads trying to push this side down. So there must be some internal force stopping that shift from happening. So now for a beam, instead of just putting some tension placeholders that we don't know what they are and solving for those internal axial forces, we can put unknown internal shear and moment placeholders and then solve this to see what it takes for this to be in equilibrium. And we can find what internal shear and what internal moment must be there to keep this in equilibrium. And we know it's in equilibrium because the whole object is in equilibrium. And that means we can then find out what that internal shear and the internal moment is in this object. I've made myself a little too big here. The axial forces in the top and bottom chord and web element of a truss can be written as a shear force and a bending moment. I am just realizing I got a brand new computer. My old computer it basically exploded on me. And if any of you have tried to order any kind of electronics, it's impossible to find anything. So I had to go on a mad scramble to try to find a new computer. But I don't have my mouse set up for you guys. So let me just, I might pause this and come back for you guys. Okay, I'm back with a mouse that shows up on the screen. I've changed it to orange since we're into October, the fall season, and Halloween is around the corner. And I do enjoy any reason to celebrate almost anything. So for the next few weeks, we'll go with an orange mouse cursor. Okay, so the axial forces in the top and bottom chord and web element of a truss can be written as a shear force and a bending moment. So instead of all of these internal axial forces, it's similar to an internal shear and a moment. Okay, let's do exactly what we did last week with a truss, but with a beam. And we're going to go through a few examples. I have, at the end of this lecture, 4 extra worked out examples that I'm not going to record as part of the lecture. I added them in last year because there are always people who like to do more practice problems. They are not required for you to do. Everything that you need to know to complete the term is listen to this and follow up until the takeaway tips at the end of the lecture. But if you feel like doing more practice problems, there are 4 more provided at the end of the lecture for you. I have, since I've took one lecture and turned it into 2 lectures, added a few components within this lecture for us though. So we are getting a few more problems that I'm solving in the lecture. So let me just turn my screen, my camera down here. Oh, it didn't like that at all. It's very delicate. All right, and I'll make this bigger for you guys. Okay, so we have a problem that we've been given. I also realize that I need to find it because I can't see my slides anymore. So we've been given a beam that has a 20 kilonewton point load at the mid-span of a 15 meter long beam. And we want to know what the internal forces are in this beam. And so how are we going to do that? Well, we know that the very first thing we have to do is figure out what it takes for the object as a whole to be in equilibrium. That is always the number 1 step. And we know that a beam is typically a pin roller condition at the end. And so we need to figure out what the reactions are that keeps this in equilibrium. So let's go through this problem. Okay, we have our beam. Let's draw our beam. It's 15 meters long. All right, and we're going to note that this is 15 meters. Remember, a free body diagram needs all the dimensions and the forces and the reactions. This beam has a 20 kilonewton point load, and we know that that is at the halfway point on the beam. They've told us that in the question. So 7.5 meters and 7.5 meters. And we know that a typical beam has a pin roller condition, or we'll call this R1, Rx, and R2. So the very first thing we're going to do is find out what all of these internal reactions are. So step 1, free body diagram. Step 2, solve for reactions. All right, we're pretty good at this now. We know that we can solve all of the forces in the y direction, the x direction, and we can pick a point to spin about. I've told you again and again and again that for solving for reactions, I'm pretty lazy, and I normally put my pin right here, or the spot that I'm imagining I'm trying to spin this about right here. So let's sum our forces in the x direction, and we want to know what it takes for this to be in equilibrium, or for the forces all to be 0. So we have Rx, okay, Rx equals 0. That one's nice and easy. Let's sum our forces in the y direction, where everything upwards is positive. Now, normally I go right to the moment equation and then do the y equation after, just because I've done this enough. I'm pretty lazy and I know a few tricks to make this go a bit faster. Well, let's see. We've got R1 going upwards, which is positive, R2 going upwards, which is positive, and we've got 20 kilonewtons going downward. And those are all our forces in the y direction. So all we really know is that R1 plus R2 equals 20 kilonewtons. Let's just take a little second here and look at this. Forget the math. If I sat at the middle of a table that was some distance apart, how much of my weight do you think was going to go to each side? I think intuitively you know that half of my weight would go to this side and half of my weight would go to this side. So I think you intuitively know that R1 is going to equal R2. And look, if my weight is 20 kilonewtons, I am not 20 kilonewtons, but if my weight was 20 kilonewtons, I'm just going to guess that that's the answer. I've done no math. I just intuitively know that if I put a 20 kilonewton weight in the middle of this beam, half of it's going to go to this side and half of it's going to go to this side. But this is just my guess up here, just because it makes life easier. I still don't have an answer here from this, so let's do some of the moments about the z-axis where everything in that direction is positive. And I'm going to pick R1 to spin about. So it's like I'm putting a thumbtack right here. R1 passes through the point and Rx passes through the point, so it doesn't cause it to spin. Our 20 kilonewtons causes it to spin like that. Or if I curl my fingers of my right hand in that direction, it tries to spin it in the negative direction. So minus 20. To be a moment, you need a force and a distance. So that 20 kilonewtons is 7.5 meters away from the point I'm trying to spin. R2 is trying to spin my paper in that direction. Curl the fingers of my right hand. My thumb is pointing upwards. That means it's positive. So plus R2 times 15 meters equals 0. I can solve for R2. Let's just check this out here. We can multiply the 20 by 7.5 and bring it to the other side of the equation and turns it to a positive. So 20 times 7.5 divided by 15 equals 10 kilonewtons. Okay, so if we plugged R2 into here, so we plugged 10 kilonewtons into here, we bring it to the other side, 20 minus 10, R1 equals 10 kilonewtons. Well, look at that. It's exactly what we predicted the answer would be. This is where I say most of the things we're doing you intuitively know, and I'm showing you the mathematical proof for those things. Okay, so this is what we learned 2 weeks ago. We're at the point we learned 2 weeks ago. Let's start doing method of sections. Now, how do we pick where we solve this? I mean, technically, we should cut everywhere along this beam. So how do you cut everywhere? Wouldn't we get an infinite amount of cuts? And yes, you're right, we would get an infinite amount of cuts, but that's crazy. We're not going to make an infinite amount of cuts. And for those of you who really like math and maybe even have a mathematical undergrad or are doing dual undergrads, know that what I'm talking about is calculus. And essentially, we're doing some calculus shortcuts, or these are based on the principles of calculus. I have had students try to solve these using calculus, and as long as they get the right answer, I am fine with it. But I am showing you the way most engineers solve these problems in methods that have been proven and are correct. So let's do step 3. Let's do method of sections. Method of sections. Cutting. And cutting where? Where are we going to cut? Well, let's think about it. I said technically we should be cutting everywhere, but maybe where nothing is happening or there's no change happening, it's not very interesting. So basically anywhere from here to here doesn't look like much is going to change. Or distance away from this point, possibly. Anywhere from here to here doesn't look very interesting. So I am, and again, this is because I'm good at this. You wouldn't know to do this, but I am going to tell you a few good places to cut. Well, obviously, let's cut maybe somewhere right there, and let's cut somewhere right there. But we should maybe also cut where interesting things are happening. I am going to suggest we cut just after the reaction. So at, a distance 0.000000000001 meters past 0. We'll get to that. I'm also going to suggest we cut on each side of that reaction and right here. So I'm going to suggest we make 1, 2, 3, 4, 5, 6 different cuts. Now, if you know anything about what I do with you guys, we're going to start to find ways to make this easier. Maybe we don't need to make 6 cuts, but let's start by doing 6 cuts and seeing what kind of answers we get. I just got a message from daycare. I have to make sure my kid isn't sick. Sorry, everyone. Sorry. All right, so I'm sorry. I have to pause this. I have to go pick up my kid from daycare. Damn it. Okay, folks. So for you, that was just the tiniest blip in time. For me, it's been a whole day, almost. I went and picked up my kids. Picked up my 3-year-old, and because he was being picked up, then I had to pick up my 5-year-old. So they're off getting COVID tests. The first appointment was this morning, available appointment. So they're off getting COVID tests. So bear with me as I jump back into the problem we were solving. Okay, when I left off yesterday, I was talking about where the heck would we cut this along its length to do method of sections. And I was explaining that technically we need to do everywhere along this length, which is sort of like what calculus is. But what if we just kind of picked a few spots and saw what happened at those? And I'm suggesting before and after anything interesting, and maybe somewhere in the middle. So, maybe let's pick 3 spots between reaction 1 and the point load, and 3 spots between the point load and reaction 2. Let's pick as close to those places where something interesting happens as possible. So let's talk about what I mean by that. So I'm suggesting let's cut at 0 meters. So right here. But when I say at 0 meters, I mean just after reaction 1 is on this beam. So really, I'm kind of saying at 0.00000000001 meters. And then I'm saying let's cut somewhere between 0 and 7.5. So at 3.75 meters. And then I'm saying let's cut at 7.5 meters, but just before the 20 kilonewtons is applied. And I know that, why wouldn't it be right at the 20 kilonewtons? But bear with me. We're going to say it's at the 20 kilonewtons, but just this side of it. So at 7.5 meters. But I'm really saying at 7.499999999 meters. So for rounding purposes, we're at 7.5. And then I'm going to say, let's cut it at 7.5 meters again. But I'm really saying let's cut it at 7.50000000001 meters. So just before the 20 kilonewtons is applied and just after the 20 kilonewtons is applied. I'm then saying let's cut it somewhere between these 2 points, or at 11.25 meters. And then let's cut it at the end, or 15 meters. But I'm saying just before this reaction. So just before we've completed the original free body diagram. So at 14.9999999 meters. So those are the places we're going to cut this beam using method of sections, knowing that if we're taking some section of it, we must have internal forces that are keeping, if this whole thing isn't moving around in space, the little section can't be moving around in space, but we only have an applied load on it, so something must be happening at that internal spot to keep it in static equilibrium. So let's take a look. Let's start with an easy cut. I'm going to pick at 3.75 meters, just because that one is probably a really easy one to get your head around. So we're going to cut it at 3.75 meters. So here is my beam. We know on the part that we're keeping of this cut, we've already solved for this reaction. We know it is 10 kilonewtons. We know that that is 0. And we know that we are cutting this at 3.75 meters. And this is what we have. Well, this looks like it wants to fly off into space, but we know it's not because it's attached to the rest of the beam right here. So there must be something that keeps this small section from flying off into space, and it's the fact that it's being held on right here. So there must be some internal load at that point that keeps that from happening. So I am going to draw the internal shear and moment placeholders that we don't know what they are, that we can solve to see what is keeping this in static equilibrium. I'm going to say I have an unknown M and an unknown V. Now, you see I drew my arrow for shear with only half of the head on it? That is just the way engineers tend to draw a shear arrow. You know how we're talking about that plane of the two things slipping by each other? That little half an arrowhead really shows that we're talking about it slipping past. It is just convention. You can draw a full arrowhead. There is nothing wrong with that. Why did I draw my arrowhead down? I don't know if my moment is positive or negative. I don't know if my shear is positive or negative. I have no idea. These are placeholders. My moment, I'm going to draw it in the positive direction. You know, remember our thumb is sticking out of the page, our right hand? I'm going to draw my moment in the positive direction. Why am I drawing my shear down? Meh, that's what I feel like. But I am going to be consistent. I'm going to recommend that you do the same thing, but you could always draw your shear up. Definitely be consistent, but you could pick either way. I am going to draw it downward. And you'll see why that shakes out nicely in a little bit. So let's do the same things we have been doing before, where we use our 3 equations of static equilibrium to figure out what internal forces keep this in place. So let's start by summing the forces in the y direction, where everything upwards is positive. And we want to know what it takes for this to be in static equilibrium. Well, we have 10 kilonewtons going upwards, and we have an unknown shear going downwards. We don't know what the value of that shear is, but those are the only things acting in the y direction. V equals 10 kilonewtons. So at this point right here in this beam, if they have a 20 kilonewton point load applied at the midpoint of a 15 meter long beam, there's going to be 10 kilonewtons of shear right here. Okay, seems like we have some information now. Let's try summing the moments about a point. Now, when we were doing our overall free body diagram, I was lazy and always picked that point right there. I'm going to mix it up on you a little bit. Because the point we pick, anything passing through that node doesn't cause a moment on it, I'm going to be kind of lazy. And I'm going to pick the point where I've made my cut as the point to spin about. Remember, I can pick any point I want. I'm going to spin it in the positive direction, or everything in that direction is positive. and I'm spinning about the z-axis, I'm going to pick the point 3.75 meters. So this is where I'm putting my imaginary thumbtack, is at the spot I made my cut. So let's see, if I put a thumbtack here, the shear is passing directly through it. That's 0 kilonewtons. We have 10 kilonewtons pushing this way. That's trying to make it spin in that direction. If I curl with the fingers of my right hand in the direction it's spinning, my thumb tells me that that is negative. So minus 10 kilonewtons, and it is 3.75 meters away. Shear is passing through it. All I'm left with is my unknown moment. So I've drawn it positive. I can rearrange this. M equals 10 times 37.5, or 10 times 3.75 equals 37.5 kilonewton meters. Remember, it's a force times a distance, so our units are kilonewton meters. It's important to always keep track of your meters, or your units. Well, look at this. We have information. So at 3.75 meters, the internal force on this beam is 10 kilonewtons of shear and 37.5 kilonewton meters of moment. Great, we have some information. Let's try another one. Let's cut at I'm going to cut it at 0. I'm going to cut it at 0. So I'm going to cut right here, just after our 1. Remember, it's really 0.000000001. So we have our beam right here. We know we have 10 kilonewtons of force acting upwards there, and that's 0. Our distance here is 0 meters. We have unknown internal moments of V, or internal forces of V and M. We can start to use our equations now. Let's sum the forces in the y direction with everything upwards being positive. We've got 10 kilonewtons upwards, shear downwards. Shear equals 10 kilonewtons. That's exactly what it was at this point right here. Interesting. Okay, let's now sum our moments about the z-axis, and I'm going to pick the point where I've cut, which is 0. And we're passing through this point, so the shear passes through it. We've got 10 kilonewtons going upwards, so spinning it in that direction, minus 10, but our distance is actually 0. Remember, we're cutting it right at that point, or just a hair after that point. And then we've got our positive moment, M equals 0 kilonewton meters. So at the start of our beam, we have no moment and still have 10 kilonewtons of shear. Okay, so we've done these first two. Let's go in order now. Let's do it just before our 20 kilonewtons is applied. So method of sections at 7.5 meters before load. So just before our 20 kilonewton point load is applied. So we have this at 7.5 meters. We know that we have a 10 kilonewton reaction here. and 0 right here. We're going to have internal forces that we don't know what they are, but we know this must be in static equilibrium, so we can solve for what those internal forces are. Sum of the forces in the y direction, where everything upwards is positive, we've got 10 kilonewtons up. We've got our unknown shear acting downwards. V equals 10 kilonewtons. So it looks like everywhere along that length, from here to here, we have 10 kilonewtons of shear. Let's sum the moments where everything in this direction is positive, and we're going to spin about the z-axis. And I'm going to pick the point I've made my cut, or 7.5 meters. So I'm putting my thumbtack right here. Shear passes through it, so it doesn't cause it to try to spin. My 10 kilonewtons tries to spin it in that direction. If I curl my fingers in the direction the 10 kilonewtons is trying to make it spin, my thumb points into the page, which makes it negative. So minus 10 kilonewtons times, to be a moment, we need a force and a distance. It is 7.5 meters away. The only thing causing a moment on this is the unknown moment, which we've drawn in the positive direction. We can rearrange this, and we can solve for a moment of 10 times 7.5 equals 75 kilonewton meters. Okay, so we're getting some good information now. We've cut our beam at a few spots. Let's now cut it just on the other side of that 20 kilonewton point load. So, step 6, method of sections at 7.5 after point load. Okay, so we're doing it just after the point load now. So it looks very much the same. We know that it's still just over 7.5 meters, but so small after that rounding, it doesn't even seem to matter. We've got 10 kilonewtons of reaction here, 0 here. We're just after our applied load now. So we've actually got our 20 kilonewtons right here. We know this thing isn't moving around, so there must be something holding it in place. We have our unknown shear and our unknown moment. Okay, we've got 3 equations. Let's go for it. You can see that we don't often need all 3 of them when we're doing these. Sum the forces in the y direction, where everything upwards is positive. We've got 10 kilonewtons upwards, 20 kilonewtons downwards, and our unknown shear acting downwards. We can rearrange this. We bring our V over here, 10 minus 20. We have minus 10 kilonewtons. Now, remember with axial, a negative meant that we had drawn our arrow wrong? Well, that means the same thing here. In axial forces, it was really important because it told us the difference between tension and compression. So this has told me I've drawn my arrow in the wrong direction, but the value of positive or negative shear is irrelevant. It doesn't have a meaning. What we care about is where it switches from positive to negative. So the absolute value of shear is what we care about as a result. And I'll show you what that means in a minute when we graphically illustrate what these values are. And that's where these graphs, remember last week we looked at axial force diagrams. These graphs are going to come in really handy when we talk about shear and moment diagrams. So let's sum our moments about the z-axis. Everything in that direction is positive, and I'm going to pick 7.5 meters again. So I'm putting my thumbtack right here. 20 kilonewtons tries to pass through the node, so it doesn't make it spin. My shear passes through the node, so it doesn't try to make it spin. My 10 kilonewtons spins it in that direction, which is negative. So minus 10 times 7.5 plus m. We can rearrange this, and we get m equals 75 kilonewton meters. Well, that's interesting. Just before the 20 kilonewton point load, we had 75 kilonewton meters. So the value of the moment didn't change, but it looks like we had a weird switch in our shear. We went from positive 10 kilonewtons to negative 10 kilonewtons of shear. Interesting. So it looks like something happened at this node. Let's do it at another spot. So method of sections at 11.25 meters. Just heard a funny noise outside. All right, we know we have 10 kilonewtons here, 0 here. We have an applied load of 20 kilonewtons here. We know that this was at 7.5 meters, and we're making our cut at 11.25 meters. We want to know what internal forces are keeping this from spinning in space. So we've got an internal moment and shear. So let's sum the forces in the y direction where everything upwards is positive. We've got 10 kilonewtons up, 20 kilonewtons down, and an unknown shear acting down. We can rearrange this and we get shear equals minus 10 kilonewtons. So the same value that we had just after the 20 kilonewton applied load. Let's sum the moments about the z-axis, where everything in that direction is positive, and I'm going to pick the point where I made the cut, so 11.25 meters. So this is where my imaginary thumbtack is going. 10 kilonewtons is trying to spin it in that direction, which is negative. So minus 10 times, my 10 kilonewtons is 11.25 meters away. My thumbtack is here. I've got 20 kilonewtons trying to spin it in this direction, which is positive. So plus 20 kilonewtons times, and my 20 kilonewtons is this distance away, which is 11.25 minus 3.75. And then we also have our positive moment, so plus m equals 0. Sorry, I should have written that down a line, but you can see that this is all one equation here. We can rearrange this, so we'll bring all of this over to the other side. I'm just going to rewrite it for you. So m equals 10 times 11.25 minus 20 times 11.25 minus 3.75. M equals, so we have 10 times 11.25 minus 20 times 11.25 minus 3.75. Sorry, what did I do here? Just 1 second, sorry. Sorry about that, team. I am also suffering from whatever my children have, so I am not in peak form today. All right, I minus 3.75 because I knew what the answer was, and I did it in my head and then wrote the answer of that subtraction. Let me rewrite this for you, okay? All right, this is our equation here. We want to sum all the moments about our point right here. We've got our thumbtack here, our 10 kilonewtons is spinning it that way. So we have minus 10 times 11.25 meters away. We have 20 kilonewtons spinning it in this direction, which is positive. And it is this distance away, which is 11.25 minus 7.5 meters away, plus our moment equals 0. We can rearrange this and we get m equals 10 times 11.25 minus 20 times, well, let's just do that right there. We have 11.25 minus 7.5 equals 3.75. We can solve for this, and we get that m equals 10 times 11.25 minus 20 times 3.75, and we get 37.5 kilonewton meters. Okay, it seems like we only have one more cut we need to make now. We're going to make our cut right before the end of the beam. So at 15 meters, but just before the support. Okay, so we're talking just before our reaction would occur. So we have a 20 kilonewton point load. We have a 10 kilonewton reaction. We know that's 0. We know that this occurs at 7.5 meters, and we're making our cut at just shy of 15 meters. And so there's an internal shear and an internal moment holding this in place, and we don't know what those values are, and we want to determine that. All right, so sum our forces in the y direction where everything upwards is positive. We have 10 kilonewtons up, 20 kilonewtons down, and our unknown shear down. We rearrange this and we get shear equals minus 10 kilonewtons. Okay, so it doesn't seem like anything has happened with shear except right at the point the 20 kilonewtons was applied. Let's sum our moments. Sum the moments where everything in that direction is positive. We're going to sum them about the z-axis, and I'm going to pick this point right here where I'm making my cut just before the reaction. And we want to know what it takes right there inside the beam to stop the beam from moving. So our thumbtack is here. We've got 10 kilonewtons pushing it in that direction. If we curl our fingers of the right hand in the direction it's spinning, my thumb pointing into the page tells me it's negative. So minus 10 times, and it's now 15 meters away. Thumbtack right here, 20 kilonewtons spinning it in this direction. So we have positive 20 kilonewtons, and it is 7.5 meters away. And then we have our unknown moment, and we've assumed it's in the positive direction. We can rearrange this, and we get that m equals 10 times 15 minus 20 times 7.5, 0. Well, this actually seems like pretty good news. We don't have moment at the ends of our beams. Do you guys remember me saying that connecting for moment is really hard and really expensive? That's really great that we don't have to do a connection at the ends of our beams to try to transfer moment somewhere. There's no moment at the end. Seems to be a lot of moment at the middle here, and we have shear at the ends, and we have reactions. So we're going to have to, at some point, get the load out of our beam into whatever is supporting it. But I'm going to tell you that that's an easy thing to connect for. So we have our forces everywhere along our beam. I I'm going to suggest let's do a little graphic representation of everything we figured out. I personally like to redraw the free body diagram. I find it somewhat helpful. So I'm going to just redraw my free body diagram here. This is 20 kilonewtons. This was 10 kilonewtons. And this was 10 kilonewtons. And that was 0. And this distance was 15 meters. And that was 7.5 meters and 7.5 meters. So here's our free body diagram again. Let's see what we can get by drawing out our shear everywhere along the length of this beam. So shear, force, diagram. All right, let's draw this beam again. So there's its length, 0 to 15 meters. I'm going to write a little summary here. At 0, V equaled 10 kilonewtons. At 3.75 meters, V equaled 10 kilonewtons. At 7.5 meters, V equaled 10 kilonewtons. But then, also at 7.5 meters, V switched to be minus 10 kilonewtons. At 11.25 meters, V equaled minus 10 kilonewtons. And at 15 meters, V equaled minus 10 kilonewtons. Let's draw that on here. So at 0, we had 10 kilonewtons. At 3.75, we had 10 kilonewtons. At 7.5, we had 10 kilonewtons and minus 10 kilonewtons. At 11.25, we had minus 10. And at 15, we had minus 10. It looks like we have a little diagram we can draw. Well, it looks like these are our internal shear forces along the length of the beam. Now, see how this is positive 10 and this is negative 10? It's important to keep track of it until this point, because look, I don't care if it's positive or negative now, but I do care where it jumps over the line. So I kept track of my positive or negative, but once I'm writing it on my diagram, as long as I've drawn it correctly, I don't need to worry about the positive or negative. What's the maximum shear force on this? V max equals 10 kilonewtons at L equals 0 and 15 meters. Oh, actually, it was at everywhere. So our worst case shear was everywhere along. I was jumping ahead one problem. The worst case shear was everywhere on this beam. Everywhere on this beam, it's 10 kilonewtons. It jumps from positive to negative at some point, but the internal shear force is the same. Okay, it'll be more clear when we do the next example too. Let's draw our bending moment diagram. I'm going to promise you that your assignment isn't going to be this hard. Pay attention to cues and see how much math you actually have to do to solve your problems. Okay, let's draw our beam again, our length here. I'm just going to remind myself that that's at 0 meters, and that's at 7.5 meters, and that's 15 meters. Okay, let's write our little summary of everything here. So at 0 meters, our moment equaled 0. At 3.75 meters, our moment equaled 37.5 kilonewton meters. At 7.5 meters, our moment equaled 75 kilonewton meters. And it didn't matter if it was before or after our point load. Our moment stayed the same. At 11.25 meters, our moment equaled 37.5 kilonewton meters. And at our support, our moment equaled 0 kilonewton meters. Let's draw this on our diagram. We had 0 here, we had 37.5 and 75, and then it looks like we came back down. So this is 0. This is 75 kilonewton meters. This point right here is 7.5, and this is 15 meters. So where is the maximum moment on this? That's right. M max equals 75 kilonewton meters at L equals 7.5 meters, which looks like the midpoint of the beam. So guys, and when I say guys, that's a gender inclusive guys. I will call a group of girls guys. I'm not trying to exclude anyone. So team, when we now know the internal forces everywhere along this beam. We know that for a 15 meter long beam with a 20 kilonewton point load at the mid span, we know what the loads are, the internal loads everywhere along that beam. We should now be able to pick a beam and see if its reduced capacity is strong enough. What if this had been PF? Remember, a little subscript F means factored. If this was a factored load, that means all of these could have a little subscript F on them. So our maximum factored shear would be 10 kilonewtons. Put our little subscript F on all of these. And our maximum factored moment is 75 kilonewton meters. So we need to find ourselves a beam that has a VR greater than 10 and an MR greater than 75 kilonewton meters. So that is going to be what we start to look at next week, is how do we find those resistances? We have now solved the one side of our equation, the load side of our equation. Remember, the reduced capacity needed to be greater than the factored load. We have now solved for internal factored loads. We can start to move on to the next part. But don't worry, we're going to do a few more examples like this, so you're not left trying to figure out what the heck I am talking about. Okay, I'm going to keep my camera turned down because we're going to jump into the next thing pretty quick. Sorry guys, my PowerPoint had slid off there. Give me just a second. Where were we? Okay, slideshow. Okay. So here was the problem we just solved. We went through, we found our reactions, and we solved for every point along this, and we solved for our shear diagram and our bending moment diagram. What if we didn't know what the values were? Yeah, this is gonna be fun. We're gonna do it without values. Don't worry, you guys aren't going to have to do something this intense. What I'm trying to do is walk you through the most complicated ones where I do out the examples. You are not going to have to do anything this complicated. But I think it's really good for you to hear me say it again and again and again so that when you do your easy ones, it becomes a little bit easier on you. Okay, so look at this. Instead of a 20 kilonewton point load, we're just going to use a placeholder P. I'm even going to draw PF, if you will. We know it's at the midspan of our beam, So half of the length, but we don't know what the length is. We're going to use a placeholder L for length. So let's go through and try to solve this problem as if everything was a placeholder. We didn't have actual values when we were solving this. So let's go through. Let's make this bigger. Okay. So step 1. Free body diagram. Always the place to start. I will tell you that when Dave has new employees come in and they have a problem to solve, the very first thing Dave says every single time is, let's draw the free body diagram. That is still how he thinks about some of the most complex engineering problems in the world. You start with your free body diagram, always. Okay, so let's draw our free body diagram. This is our length. And we're going to have a load applied halfway along the length. We don't know what that load is. Let's call it PF. R1, R2, Rx. Well, let's make our usual prediction. If this load PF is in the middle of this beam, oh, okay, I didn't draw it. I drew it to the length line. How much of the load do you think is going to go to each side? Yeah, we've been here before. We know that R1 is going to equal R2, and it's going to equal half of PF. But we just intuitively know that. How about we try the math and see if that is what we end up with? Because that's going to be really important. This is where knowing intuitively what the answer is really helpful for simple problems, because we can prove it to ourselves, and then we can use that proof for the ones that maybe aren't as easy to intuitively figure out. So, step 2, reactions. All right, we know that we can sum all the forces in the x direction. So Rx equals 0. Let's sum the moments with everything spinning in that direction being positive, but the z-axis, and I'm going to pick R1. I'm going to put my thumbtack right here. Okay, so if I'm putting my thumbtack right here, R1 passes through it, Rx passes through it, Rx should be right here. PF is spinning it in that direction. So we curl our right hand fingers, and we see that PF is spinning it in the negative direction. So minus PF times half of L. That's how far away it is. It's half of L away. We've then got R2 spinning it in that direction, which is positive. So plus R2 times our full distance L away. And those are the only things trying to make this spin. Okay, so we have R2 times L. We can bring this over here. It's going to be positive 1/2 PFL. So I'm just going to rewrite that for us. So R2L equals 1/2 PFL. Well, we've got L on both sides. Let's divide out by RL. So R2 equals 1/2 PF. Great, that matches what we thought up here. Now, let's sum our forces in the y direction with everything upwards being positive. We've got R1 going up, we've got PF coming down, and we've got R2 going up, but we've already solved for R2. All right, so minus PF plus half of PF gives us minus half PF. We bring it over to the other side. R1 equals 1/2 PF. Perfect. That's exactly what we thought the answer should be. We've done it mathematically. All right, let's talk about where we're going to cut on this. We don't know what the dimensions are of this, so anywhere we cut is kind of an unknown value. And we're going to label our cut, and we're going to call it X. So we're going to call any cut we make X, because we're cutting along the X-axis. Well, remember last time we cut right here and right here and right here on this side of the beam? Well, if we don't know what the dimension is, that's X, and that's X. So we're going to cut at X for anywhere where X equals 0 to 1/2 L. And then we're going to do the same thing on the other side at X where it equals 1/2 L to L. I'm going to write 2 so you don't think it's an actual equation. So we're only going to make 2 cuts now. We're going to use a placeholder representing a cut anywhere along here, and we're going to make a cut representing a placeholder anywhere along here. Let's see how that shakes out. Step 3, method of sections for X equals 0 to X equals 1/2 L. All right, here's my cut, the section that I'm going to look at. I know that for this thing not to be moving, I have a reaction here, all R1, but I've already proven that R1 equals 1/2 PF. I know that equals 0, and I have nothing applied anywhere along this part of the beam. So I know this isn't moving in space because this isn't moving in space. So there must be internal forces that keep this from moving in space. We've cut this at some dimension X. We don't know what it is, but X can be anywhere from 0 to 1/2 L. All right, let's sum our forces in the Y direction where everything upwards is positive. We've got 1/2 PF going upwards. So 1/2 PF is positive, minus V, those are the only 2 things in the Y-axis, equals 0. Well, look at this. V equals 1/2 PF anywhere along this half of the beam. Do you remember when we did it with numbers? When we did it at 0 and 3.75 and just before 7.5, we got 10 kilonewtons and PF was 20. So this seems to check out with what we just did here. Matches our last problem. Let's sum the moments about the z-axis where everything spinning in that direction is positive, and I'm going to spin it about the point where I'm making my cut, or at X. And I want to know what it takes for this to be in equilibrium. Okay, I've got a thumbtack right here. My 1/2 PF is trying to spin it in that direction, which is negative. So we've got minus 1/2 PF times our unknown distance X. V passes through the node that we're spinning it about, so it doesn't cause it to spin. M does. We curl our fingers of our right hands. Our thumb is upward, so it's positive. We rearrange this. M equals 1/2 PFX. Remember in our last problem when X was 0 and PF was 20, 0.5 times 20 times 0, we got 0. When it was 3.75, we got 37.5. When it was 7.50, we got 75 kilonewtons. So look, this looks like an easier way to solve this. As much as, yeah, it's a pain in the butt doing it with placeholders. Look, we've already replaced 3 method of sections with 1 cut. Let's do the other side of the beam now, where we have that point load, after we have that point load on it. Step 4, method of sections where x equals 1/2 L to L. So anywhere on this side of that beam now. Let's draw our beam. I'm gonna right now mention that that is dimension X. We're cutting it after our point load of PF, and we know that this dimension right here was 1/2 L. We have our reaction of 1/2 PF, and that is 0. Sorry, I need to take a drink of water. I have such a sore throat. Sorry, everyone. Okay. This thing should not be moving in space because it's part of this thing that isn't moving in space. So there must be internal loads that are keeping this thing from flying off into space on us. We don't know what the values are, but we know there must be an internal shear and an internal moment if they have values. So let's sum our forces in the y direction where everything upwards is positive. We've got 1/2 PF going up, and we've got PF going down. And we have our unknown shear going downwards. If we rearrange this, V equals minus 1/2 PF. That matches what we saw in our example with numbers. It was minus 10, or a negative half of 20 kilonewtons everywhere on its length on that side of the beam. Let's sum the moments about the z-axis where everything in that direction is positive, and I'm going to do it at node X. I'm going to pick right here. All right. This one is going to be a little more fun. I'm going to write it down here so we have a bit more space. So we're holding our thumbtack right here. Our reaction is trying to spin it in that direction. We know that that is negative. So we've got minus 1/2 PF times X. So it's X away. We have PF, which is trying to spin it in that direction. Curl our fingers like that. That is positive, so it's plus PF. Now PF is only this far away. That distance is X minus 1/2 L. So X minus 1/2 L. Okay, all right, so this is looking a little more intimidating than some of our other questions. We've got a thumbtack here, and our fingers curl in this direction, so it's a positive moment equals 0. Let's rearrange this. Let's do this slowly. So we've got M equals, we'll bring this over, and it'll be a positive. So we've got 1/2 PFX. We're going to bring all of this over here, and we have to change the symbols. Or let's do minus PF times X minus 1/2 L. Let's multiply this out. So M equals 1/2 PFX minus PFX plus 1/2 PFL. Okay, so let's start to pare this down a little bit. We've got 1/2 PFX and PFX. M equals minus 1/2 PFX plus 1/2 PFL anywhere along the length of this beam. And that will give us our value. Great. We've got some equations. We've got things, we've solved these. We've got our answers for everything. So let's make a little summary though, because this doesn't really tell us anything. Like, we have numbers, we have equations, but it doesn't mean anything to us. Let's go through and take a look what that would look like. I'm going to write a little summary here. So summary. I'm going to do my dimension, and then I'm going to write my equations, and then I'm going to start to break it out a bit. So this is x. So at x equals 0 to 1/2 L, we have shear and we have moment. So it didn't matter anywhere along there, V equaled 1/2 PF. And M equaled 1/2 PFX. At x equals 1/2 L to L, we have our equations here that we found. V equals minus 1/2 PF and minus 1/2 PFX plus half PFL. Okay, V equals minus 1/2 PF, and M equals minus 1/2 PFX plus 1/2 PFL. All right, it's going to get a little bit easier. Don't worry. Don't get too intimidated. So let's do it at x equals 0. Let's do it at 1/4 L. Let's do it at 1/2 L. Again at 1/2 L, but just on the other side. Let's do it at 1/2 L when it's part of this equation, and then 1/2 L when it's part of this equation. Let's do it at 3/4 L, and let's do it at L. So when x equals 0, we get to use this equation, which is 1/2 PF. So shear equals 1/2 PF. M, if x is 0, is 0, because x would be here and knock everything out. At 1/4 L, we're using these equations. So 1/4 L, it doesn't matter. We're 1/2 PF, doesn't change the value. We can plug 1/4 L into x. We have 1/2 times 1/4 gives us 1/8 PF L. So 1/8 of P times L. Let's just check that out. When we had 20 kilonewtons and a length of 15, 1 divided by 8 times 20 times 15, 37.5. That's exactly what we did when we worked it out by hand. Okay, let's do 1/2 L, but on one side of the beam, on the left side of the beam. It doesn't matter, our shear stays the same. It's not dependent on x. So 1/2 L being plugged into x, we have 1/2 PF times 1/2 L. So half times a half is 1/4, 1/4 PFL. Or that would be, in our last example, 1/4 of 20 times 15. So 0.25 times 20 times 15, 75 kilonewton meters. So that seems to match up. Let's look at the other half of the beam now. So we have 1/2 L being plugged in here. Doesn't matter. It's minus 1/2 PF. All right, let's plug 1/2 L into this. So minus 1/2 PF times x, or minus 1/4 PFL plus 1/2 PFL minus 1/4 plus 1/2 equals 1/4 PFL. So we get the same value at the midpoint no matter what side of the beam we're at. Let's plug in 3/4 L. Doesn't matter, we get minus 1/2 PF. So we plug 3/4 in here, we get minus 3/8 PFL plus 1/2 PFL gives us 1/8 PFL. And then L minus 1/2 PF because it's not dependent on X. And then if we plug L into here, we have minus 1/2 PFL plus 1/2 PFL. We get 0. Huh, okay. Still, this is handy. It helps us out a lot, but it doesn't tell us things quickly at a glance. I wonder if it would help us if we graphed this out. So let's draw the graph of this. I'm going to redraw my free body diagram because I always like to draw out a free body diagram. We have R1 and R2 and Rx. And we have PF. And this is L. And that's 1/2 L. And that's 1/2 L. Well, the very first thing we determined was that R1 equaled R2 equaled 1/2 PF. And we determined that Rx equals 0. So it doesn't matter what the value of L and PF is, we determined that to be a truth. We also figured out all of this. Let's draw a diagram of that. So this was our free body diagram. Let's do our shear force diagram. All right. At X equaled 0, we were at 1/2 PF. Didn't seem to matter where along there we did it. We were at 1/2 PF. And then we jumped down to negative 1/2 PF. Remember I said once we get to this point of graphing it, it's absolute values. I don't care. So this is 1/2 PF, and this is 1/2 PF. So we're talking about a factored load, so VF max equals 1/2 PF. And it occurs anywhere on the beam. Let's do our bending moment diagram. All right, we have all of these values right here. If this is 1/4, we know that this is 1/4 PFL. So the maximum shear, so MF max equals 1/4 PFL. It looks like now we never need to go back and solve one of these. We've got the answers. If we know what PF and L is, look at this, we can just use these equations. We want to know what the reactions are. We want to know what the maximum shear is. We want to know what the maximum bending moment is. We don't need to go through this process. We already have the answers worked out right here for us. Let's take a look at what we have next. Okay, so we have our reactions. Here is that all worked out. Let's jump in to the next problem. Okay, so this was super handy. We now never have to solve by method of sections a simply supported beam with a point load at the midspan. We've done it. We've worked that out. But that's just one type of beam. The most common type of beam we will ever solve is a simply supported beam with a uniformly distributed load along its entire length. So let's talk about how we solve something that's a uniformly distributed load. Remember, if you remember, that is, if I had, here's a good way to show it. I've got a series of pens here, and I set this paper down on it. Each one of these pens is picking up half of the distance on each side of them. So this beam right here is picking up all of this piece of paper. So everywhere along its length, it's picking up a tiny little bit of load until it gets all the way to the end. That is a uniformly distributed load. Now, a free body diagram of an element with a uniformly distributed load shows the uniformly distributed load. But that can be tricky to solve. So sometimes what we'll do is we'll do an analogous point load in the centroid of the load to help us solve the problem. So we use these to represent distributed loads as an equivalent point load to simplify the diagram. It still has the same effect on the equilibrium of the free body diagram, so also the reactions. But you can't use the same analogous point load at each section cut. It is dependent on the cut you're making. So let's take a look what I mean by that. If this gray zone is representing our uniformly distributed load, this one isn't along the full length. Where's the centroid of this? Yeah, you know that it's at the middle of D. Not the middle of the beam, but at the middle of D. And you know that if you were going to represent this as a single load, you would say, okay, that is D times W. What would be something similar to that? Something similar would be me laying down on the table, but it's a really, really, really long table. So this is the entire weight of Shannon spread out over the table. So there's a little bit of Shannon over this length of table. If I then sat up and stood in the middle of where I was supposed to be, I would stand up right here and all of my weight would be right here. That is a similar thought process to analogous point load. So we could represent this with this in solving for our equivalent free body diagram. So the analogous point load of a triangular distributed load. If you guys remember, the centroid of a triangle is at the 2/3, 1/3 mark. And the area of a triangle, or the volume under this triangle, is the height times the length divided by 2. So this would be the analogous point load for this distributed load. Okay, that was all just a handy little thing to jump into what I'm going to do next. This is, without a doubt, the most important beam ever in the history of the world. Now, sounds like I'm being a bit melodramatic, but I'm not. This beam that we're looking at right here represents probably 95% of beams you will ever solve. We have an unknown uniformly distributed load called W. So every meter of this beam has W kilonewtons on it. So if W was 1 kilonewtons per meter and this was 1 meter long, we'd have 1 kilonewton. If this distance was 2 meters long, we'd have 2 kilonewtons, with a kilonewton at every meter along its length. We're going to solve this with placeholders though. We don't know what these values are. We're going to use W as a placeholder, and we have some unknown length L. Let's see what we get with this. I see my children, my husband coming back with my kids. They just came back from getting their COVID tests, so you may hear a bit of noise in a minute. Okay, I'm going to take a drink of water. Okay. I like that I'm getting to spend more time solving these problems with you, because this one was a bit of a rush if we were trying to jam it all into 1 week. I've done it, but I think I like this better. Okay, let's start with our free body diagram. All right. I like to draw it always the same length just so it represents itself nicely. All right, we have our unknown length L. We have a uniformly distributed load all along its length, W, and it's in kilonewtons per meter. L is in meters. And we have R1 and R2 and Rx. Let's just do our usual little thought experiment. When I was sitting in the middle of the table, we knew that half of my load went to this side and half of my load went to this side. Intuitively, we knew that. If I spread myself out evenly all over the table, do you think more of my load goes to this side? More of my load goes to this side? Or do you think, again, half of my load goes here and half of my load goes here? I think you intuitively know, and we're going to make this guess, that R1 equals R2, and it's going to equal half of the total load. But we don't know what the total load is yet, but we do know that the total should be the length times W. So let's cross that out and call it WL. So we think reaction 1 and reaction 2 should each be half of the total load. We have a bit of load everywhere along its length, or W kilonewtons per every meter, and we've got L meters. So we should have WL as our total load. All right, let's solve for our reactions. Now, to solve for our reactions, we need to use analogous point load. Analogous point load. Oh my goodness, hold on a second. My kids are banging on the door. Oh, hold on, I'll be right back. Yes, buddy, we're recording a lecture, okay? So you have to stay over here, okay? I'm recording a lecture. All right, buddy? I'm teaching. Okay, sorry, everyone. Sorry. It's a pain in the butt when I stop it. I have to stitch the videos together, so I don't like stopping the videos if I don't have to. Okay. So we are going to solve for our reactions, and this is where we're going to use our analogous free body diagram. It is not the actual free body diagram. It's just kind of a fake free body diagram that we're going to use to help us out. So we have this, and at the midpoint, we have our point load, P, which is W times L. Because remember, every meter along this length had W kilonewtons on it, and we have L meters. So W times L is our total load. R1, R2, Rx. We are L meters long, and both of these are 1/2 L and 1/2 L. This looks pretty darn similar to what we had done before. But this is just a representation to help us find the reactions of this condition. We know that really there's a W kilonewtons at every meter along this length. So it's not going to be the exact same answer, but for this part of it, for finding the reactions, it should be the same because we know half of the load should end up on each side. So let's see what we get when we do this. So we sum the forces in the x direction. We get Rx equals 0. Let's sum the moments about the z axes where everything in that direction is positive, and I'm lazy. I'm going to pick R1 as where I spin my node about. We've got P spinning it in this direction, so we curl our fingers like that. P that's a negative value, so minus P, but P is really WL. And WL is happening 1/2 L away from the point I'm trying to spin about. R2 is trying to spin in this direction. So we've got L away, it's spinning in the positive direction, so we've got plus R2 times L equals 0. Okay, remember R2 is what we want to find here. we've got R2L equals 1/2 WL squared. We can divide both sides by L. R2 equals 1/2 WL. Huh, look at that. 1/2 WL. That's what we thought we should get, so we're feeling pretty pleased with ourselves. Sum of the forces in the y direction, where everything upwards is positive. We've got R1 going upwards. We've got WL going downwards. And we've got R2 going upwards, which we know is 1/2 WL. So we end up with minus 1/2 WL here. We bring it over to the other side. R1 equals 1/2 WL. Perfect. That matches our prediction, and it's exactly what we expected to see. Now, let's cut our method of sections. So, method of sections, where X, we're going to use a placeholder X to cut somewhere along this length. It looks like there are changes happening everywhere along the length of this, but it looks like the change is the same. So it's not just about where does a change happen, but where does the rate of change happen. My husband's backing up the trailer and it freaks me out when he doesn't have, where are the kids? It stresses me out. I'm going to stop this because I want to see where my kids are. I need to know where they are. Okay, crisis averted. One kid was in the car with him. The other one is inside playing with toys. All right. So we want to cut somewhere along this length, but what we care about is everywhere there's a change happening. Well, there's a change happening everywhere along here, but at least it looks like the rate of change is the same. Every kilonewton, every meter, another W of kilonewtons is added to this. So let's treat it as we're going to cut anywhere along this length because we know that the rate of change should be the same. So we're going to look at a cut at X where X equals 0 to L. So one cut, we're going to take a look at what that does to anywhere along the length of this. So let's draw this. We know that our reaction, we've already solved for this, is 1/2 WL. We're cutting at X along the length. And we know, Malcolm, stay inside. Malcolm. Sorry, everyone. Let me pause this for a second again. I'm really, really very sorry, but having small kids when you're trying to teach. Okay, sorry, everybody. My 5-year-old is having a meltdown because he didn't get to go in the car while my husband moved the trailer. And then my 3-year-old is mad because he fell out of the car getting out at the end. So, you know, things are okay. It's all right. We're all good. We're gonna make it through this. All right. So we have our load here that we know is W. So this is our load W. We're cutting it at X. We know what our reaction is. And we know something must be keeping this in place. Some unknown shear and some unknown moment. But I've told you it's a real pain in the butt trying to solve these things with a uniformly distributed load on it. It's super handy to use an analogous point load as a handy little trick. This is still the free body diagram of this section, but we can use an analogous point load to help us out just a little bit. So we still are cutting this at X. We still know that our reaction is 1/2 WL. We still know that we must have an unknown shear and an unknown moment that are holding these in place. But now we're going to use our analogous point load that is happening on this portion of the beam. So we have this portion right here is P, but P is W times whatever the length of this beam is. And the length of this beam is X. So it is WX. So the amount of analogous point load is W times the length we have there. So imagine that analogy where there was me spread out all over the table. We're cutting the table, and it's the portion of my load that is on that part of the table. All right. This is now what we're going to solve. And remember, I always like to put my thumbtack there when I get to that point. Okay, let's sum the forces in the y direction, where everything upwards is positive. So everything upwards is positive. We have 1/2 WL going upwards. So 1/2 WL upwards. We have P going downwards, which is negative, so minus WX. And we have V going downwards, so minus V. We can rearrange this, and we have V equals 1/2 WL minus WX. Okay, so we have an X in our equation now. It looks like V is dependent on where along the beam it is. So we've solved for what we can here. Let's sum the moments about the z-axis where we spin everything in that direction, and let's pick our cut point right here, or X. All right, we put our thumbtack here. 1/2 WL spins in that direction, which we know is negative. So minus 1/2 WL times the distance we are away, which is X. I'm going to just put that in brackets. Maybe it'll help us keep track of things. And then we have our WX, our force WX. Here's our thumbtack. We're spinning our paper like that. It's spinning it in the positive direction. So plus WX times, now the distance away here, both of these are 1/2 X. So this is times 1/2 X away. We've got our thumbtack here. M is spinning in the positive direction. Remember, I didn't know. I took a guess. I said M is positive. And all of that equals 0. Let's rearrange this. All right, we have M equals, we'll bring that over and make it positive, 1/2 WLX. This is going to come to the other side and be negative. We have minus 1/2 WX squared. Oh, we've got a quadratic in here. Fun. So M equals 1/2 WLX minus 1/2 WX squared. So we've got some information here. That's it. This one's like really easy. It seems really overwhelming, but it's not so bad. Let's do the same thing we did last time. Let's look at X in meters. Let's look at shear kilonewtons, and let's look at bending moment in kilonewton meters here. Okay. We know that at X, V equals, we've solved for it right here, 1/2 WL minus WX. And we know that M equals 1/2 WLX minus 1/2 WX squared. All right, let's try it at X equals 0. So let's plug 0 into this for X. So this goes away. We end up with 1/2 WL. If we put X as 0 into here, this side of the equation goes away and that part of the equation goes away, our moment equals 0. Let's look at x equals 1/2 L. So let's plug in 1/2 L, so the middle of the beam. All right, we plug in 1/2 L for this. We have 1/2 WL minus, remember x is 1/2 L, minus 1/2 WL. It looks like our shear is 0. We plug in 1/2 L for x. We get 1/2 WL 1/2 L. So 1/2 WL, or 1/4 WL squared, minus 1/2 W 1/2 L squared. So L squared 1/4. So 1/2 times 1/4 is 1/8, and we had 1/2. If you work it all through, you end up with W L squared divided by 8. What about when x equals L? So at the other end, we plug L in here. We have 1/2 WL minus WL. We end up with minus 1/2 WL. If we plug L in for x, we end up with 1/2 WL squared minus 1/2 WL squared, or 0. Now, you could go through and do it by plugging in more points on this, but I'm going to show you what this looks like. So, free body diagram. We had our uniformly distributed load going along. Rx, R1, R2. This is W in kilonewtons per meter. This is L in meters. We solved for this and we got that R1 equals R2 equals 1/2 WL, and that Rx equals 0. So we've solved for this. Let's do our shear force diagram. All right, we have our length L. We know that we have an equation and we've plugged in a few points. If we wanted to, we could go through and plug in those points as well, and we would calculate those as well. That would be 1/4 WL, and that would be minus 1/4 WL. But this is 1/2 WL. This is 0, and this is 1/2 WL. Remember, it's negative, but we don't care so much when it's shear when we get to that point. What we care about is the absolute, and that's in kilonewtons, and that's in kilonewtons. So if W was WF, we would know that we can figure out what the maximum shear force is on this. So V max equals 1/2 WL. And that occurs at midpoint. Oh, sorry. At ends. V equals 0 at midpoint. So you could even say at the supports. So we have some interesting information here. Let's look at our bending moment diagram now. All right, the equation was a quadratic, so it's not a perfect circle, but if we went through and plugged in, we figured out those points. I'm going to tell you that if we went through and plugged in a few more points, it would start to look like this. Did I draw that? I haven't drawn it very well, but it would be the equation of a quadratic, and this is WL squared divided by 8, and it's 0 and 0 here. And we're in kilonewton meters. So our M max equals WL squared divided by 8, and that is at the midpoint. That is a super important equation. Engineers, I plug that into my calculator all the time. WL squared divided by 8. W is the load accumulating on my beam every meter. Okay, so I've said that this is the most common beam we design. We've just solved it. It doesn't matter what W is or what L is. We can figure out what the maximum shear and the maximum moment are. And we know where those things occur. We can even calculate the reactions. So it seems like we've just done most of the engineering that engineers need to do. We just did it, like in the last half of one lecture. So let's go through. I have that all here for you worked out. So you have that. So equations for a uniformly distributed load on a simply supported beam. Using method of sections, we develop the equations that find the reactions and the shear or bending moment at any point on the simply supported beam, as well as the maximums. So we know what the reactions are, and we know what the shear and the bending moment are. Vmax is WL divided by 2, and Mmax is WL squared divided by 8. Those are two of the most common things engineers plug into their calculator. Well, if we did this, it seems like other people might have done some other problems. So we just did this, like this handy little thing that's published in all kinds of books, we've just done. The reaction equals the shear equals WL divided by 2. M maximum at the center point is WL squared divided by 8, right there. There's some other stuff here. Some of that's a bit beyond us. Ooh, delta max at the center, 5WL to the 4 divided by 384 EI. Maybe we'll use that later in the term, but I'm not going to make you prove that yet, but that's going to be handy. We'll come back to that later in the term. But right now we calculated this and this as well. So we have just hand calculated all of that, and now they have a handy table for us. Well, look at this. They have handy tables for all kinds of other beam layouts. Look at this beam, a concentrated load at any point along the beam. I wonder if assignments and quizzes would come back to this, and maybe, just maybe, you don't have to go through and do the full complicated method of sections calculations. Maybe you could use these handy charts. Remember, you're turning in the final result. I'm not seeing what method you're using to do it. If I am telling you that I look these things up on these charts, why shouldn't you be able to look these things up on the charts? Look at this, a uniformly distributed load on a beam with a cantilever. Okay, I'm going to do one more fun problem with you just because we have a few more minutes left. I'm going to do the moment frame version of the braced frame we did last week. I hadn't normally done this in the lecture, but since we've split it up into 2 lectures, I think this is a good fun one to do. I do want to show you that I have a bunch of bonus examples here for you that if you would like, I have it worked out using method of sections, but then also showing how we would use the tables to do it as well. So if you are a person that likes to do more problem sets, they've been provided for you, but by no means do you have to. I feel like most people have enough information that they could proceed without doing these. It depends on what my mood is. Sometimes I'm the sort of person that likes to do more problems. Sometimes I'm not. And so here's another one. Here are a few more that you can do. Okay, I am going to solve this moment frame. Now, this is not statically determinate. Statically determinate means technically, we cannot use, we don't have enough to solve this. So look, this is a pin and a pin. Remember, a pin has an unknown y and an unknown x component. This is not a pin roller. It's a pin-pin, which means we have a y reaction, an x reaction, and an x reaction. That is 4 unknowns. How many equations do we have in the 2D problem? We only have 3 equations. You need as many equations as you have unknowns. Now, let's think about this for a second. If you had all of your weight centered evenly over yourself and someone was pushing you along the ice, do you think the friction on your feet would be equal? I tend to think, yeah, they would be equal. There's nothing else happening. You're just being pushed along. Both feet would be resisting the same amount of load in the x direction. So this is just something we know intuitively. This is an assumption we're making. I can tell you that I'm giving you a problem where that is the case. Later on in the term, I am going to show you some slides that indicate when or what happens to this same problem that I'm doing when that wouldn't be true. And that is called a statically indeterminate problem, where we have to iteratively solve it, which means what I'm about to do for this moment frame, if it was a different type of moment frame where we had different stiffnesses in our beams, we would see that assumption we're making for this one would not be true. And we would have to solve the problem multiple times, honing in on our answer. We would make an assumption that we knew was wrong, and then we would make an assumption at the other end of the spectrum. And then we would start to come in and tighten our answer up. And that's called solving a statically indeterminate problem. We're just going to make an assumption that reaction X and reaction X are equal. So let's go through and solve this moment frame problem, just for fun. Some of you might just want to turn me off now. This is just a bonus extra problem that I'm going to solve for you because I really like this one. Let me, I need to, sorry. 1 second here, my phone is doing weird things. I'll be right with you. I'm not ignoring you. Okay, it's all right. Okay, so we have here our moment frame. Now remember, moment frame means that there's moment connections at the corner. So it's not like we have moment released. So instead of moment being released where it can swivel, we've got it locked in tight. So instead of this being able to do this, we're saying that these are glued together. And so for this to push over, it can't rotate here. These 2 points cannot rotate relative to each other. They're glued together. They have to stay at a right angle. So we have a frame that is 5 meters tall and 8 meters wide. And these are essentially glued together here. We have a load of 250 kilonewtons applied right here. We know that our frame is 5 meters tall, 8 meters wide. It was pin supported at both sides. So we have RY1 and RX1. We have RY2 and RX2. I am making the assumption that RX1 equals RX2. And we're going to go through and solve this. Let's do my little trick where I number things and label them. So we're going to call that node 1, 2, 3, 4, and this is member A, member B, and member C. So I'm going to go around the system. First, I'm going to solve for the reactions, and then I'm going to go around the system and find the internal loads everywhere in this moment frame. So reactions. All right, we can, sorry. All right, we can sum the forces in the x direction. So everything in that direction is positive. We have Rx1 and Rx2, but I've said Rx1 equals Rx2. So really we have Rx2 plus Rx2 equal, or plus or minus 250 equals 0. Or 2 of Rx2 equals 250. Rx2 equals 125 kilonewtons. And Rx equals R1, or Rx1 equals Rx2. So these both equal 125 kilonewtons. Let's sum the moments about the z-axis, and let's pick node 1. Everything in that direction is positive. We're going to put our thumbtack right here. Ry1 passes through the node. Rx1 and Rx2 both pass through the node. So we have Ry2 and 250 kilonewtons. Both are trying to spin this in this direction, which is positive. So we have plus Ry2, and it is 8 meters away, and we have our 250 kilonewtons passing along that way, and it comes 5 meters away. So plus 250 times 5. We can rearrange this, and we get Ry2 equals 250 times 5 divided by 8 equals, now that would come over there and be negative, minus 156.25 kilonewtons. So I've drawn this in the wrong way. It makes sense that as this frame tries to push over, this side wants to lift up. So we've got to be holding this side down. Okay, let's sum our forces in the y direction where everything upwards is positive. We have Ry1 is upwards. We have Ry2 going upwards, but it's minus 156.25 equals 0. Ry1 equals 156.25 kilonewtons. So we have all our reactions. We have R1, or Rx1, Rx2, Ry1, and Ry2. So we have all of our reactions for this moment frame. Now we can start to do cuts where we solve for the internal forces. Again, this is way beyond anything you're going to have to do, but seeing me do a hard one, I think helps make the easy ones even easier. So let's cut along A. So we're going to do a cut somewhere along member A. So here's our member A that we're cutting. We have a reaction of Ry1 here equals 156.25, and we have Rx1 is 125 kilonewtons. Well, that's interesting. Looks like we have two different reactions here. We have things going in different directions. We're cutting x distance away, and we have unknown internal loads. We also now have an unknown internal axial load. So we have an unknown shear, we have an unknown moment, but we also have an unknown internal axial load, A. I'm going to draw it in tension because I don't know if it's in tension or compression. If I get a negative number, I'll know it's actually in compression. And remember, positive versus negative is really important for axial loads. It's important for moment and shear to help keep track of things, but a lot of times the absolute is more what we care about. All right, let's sum the forces in the y direction, where everything upwards is positive. Well, we've got RY1 going upwards, which is 156.25, and we've got A going upwards. We rearrange this. A equals minus 156.25 kilonewtons, or A equals 156.25 kilonewtons in compression. So A is in compression. Let's sum the forces in the x direction, where everything going in this direction is positive. We have 125 kilonewtons going in the positive direction, and we have our unknown shear going in the positive direction. It looks like V equals minus 125 kilonewtons. So member A has an axial load and a shear in it, and it does not look to be dependent on where along the height of A it occurs. It is just an absolute value. Anywhere along A, the shear is 125 kilonewtons. Anywhere along A, it's 156.25 kilonewtons in compression. Let's sum the moments going in that direction about the z-axis, and let's cut at x. So we're cutting at this node here. The shear passes through it, the axial load passes through it, the reaction Ry passes through it. We're left with 125 kilonewton reaction and our unknown moment trying to make it spin. So 125 kilonewtons spins it in that direction. Curl our fingers in the direction it tries to spin. It's positive. So we have plus 125 kilonewtons times our distance x. I'll do a dot for that. And then we have our moment. So we have m equals minus 125x kilonewton meters. So as you go up the height of this beam, we are having a varying moment. So let's just write what that means for us. So we know anywhere along the length, the axial force doesn't change. Anywhere along the length, the shear force doesn't change. What is it at x equals 0? So at the bottom, if x is 0, m equals 125 times 0, m equals 0. What about at x equals 5 meters? Remember this beam was 5 meters tall. M equals negative 125 times 5 equals minus 625 kilonewton meters. So we know the internal loads on member A. Great. Let's do our next cut. Let's cut along B. So we have 1, 2, 3, 4, 5. We're going to cut along B. We know this is 156.25 kilonewtons. We know this is 125 kilonewtons. No other internal loads happen on this. We know that this is 5 meters. And we know that this is x. This is member B, so there could be an unknown axial force. I'm going to draw it in tension because I don't know what direction it is. I have an unknown shear and an unknown moment. So now I can use my 3 equations to solve for what is stopping this moment frame from flying off into space, or what it takes for this to be an static equilibrium. So sum of the forces in the y direction equals 0, where everything upwards is positive. Okay, we have 156.25 upwards minus V because it's downwards. Oh, V equals 156.25 kilonewtons. Okay, anywhere along its length, the shear is 156.25 kilonewtons. Let's sum the forces in the x direction. Okay, in the x direction, we've got 125 kilonewtons going that way, plus our unknown axial B load. Well, we rearrange this. B equals minus 125 kilonewtons, or B equals 125 kilonewtons in compression. Okay, let's see, we have one more equation for us. Let's sum the moments about the z-axes, and let's pick my node x where I cut to do this. So I'm putting my thumbtack right here. I like that because B passes through it and my shear passes through it. But now look, I have a 125 kilonewton component and 156.25 that are both trying to make it spin. And my unknown internal moment. So my unknown internal moment is positive. So I have M. 156.25 is trying to spin it in that direction, which is positive. So plus 156.25, and it passes x distance away. So times x. And 125 kilonewtons tries to spin it in that direction. Oh, sorry. My 156.25 is actually negative. Plus my 125 kilonewtons, which is spinning it in that direction, which is positive. And it is happening 5 meters away. So we can rearrange this, and we get M equals 156.25x minus 125 times 5, or 625 kilonewtons. So let's plug two of these in. Let's see at x equals 0. So back at this end of the beam. At x equals 0, we can plug that in, and we get 156.25 times 0 minus 625. So at x equals 0, M equals minus 625 kilonewton meters. What about at x equals 4 meters? M equals 156.25 times 4 minus 625. M equals 0. And what about at x equals 8, which is how long the beam can be? B can be up to 8 meters long. M equals 156.25 times 8 minus 625 gives us a positive 625 kilonewton meters. Well, now we know what the internal loads are on B anywhere along its length. Let's do one more cut. Let's cut along C. One, two, three, four, 5. Okay, we're cutting along C. We have 156.25 kilonewtons here, 125 kilonewtons here. We now have 255 kilonewtons of applied load there. This distance is 8 meters. This distance is 5 meters. And this distance is x. I don't know if this member is in tension or compression, but I'm going to assume it's in tension. So C, I am going to draw my shear and my unknown moment. So now I can solve for the internal forces in member C. So let's sum our forces in the y direction where everything upwards is positive. So we have 156.25 kilonewtons upwards minus C, because it's downwards, equals 0. C equals 156.25 kilonewtons in tension. Let's sum our forces in the x direction, where everything in that direction is positive. We have 125 kilonewtons going that way. We have 225 kilonewtons going that way. And we have V going that way. All right, we can rearrange this, and we have V equals minus 125 kilonewtons. All right, one more unknown, one more equation. Sum the moments about the z-axis. Everything spinning in that direction is positive, and I'm going to spin it about point X, so right here, but remember, X is from the top down. We have our thumbtack here. C passes through it, V passes through it, M tries to spin it, but we've got 250 spinning it that way, 125 spinning it that way, and 156 spinning it that way. I'm going to write it down here just so I don't lose track. Okay, moment is positive. All right, thumbtack here, we've got 156.25 kilonewtons spinning it in that direction. That is negative. So minus 156.25 times 8 meters. We have our 250 kilonewtons spinning it in that direction, which is positive, so plus 250 kilonewtons, and it is acting X away. We have our 125 kilonewtons, which is trying to spin it in that direction, which is also positive, and it is this distance away, or 5 meters minus X. So 5 minus X. Okay, we have M minus, let's do 156.25 times 8 equals 1,250 plus 250x plus 125 times 5. 125 times 5 equals 625 minus 125x equals 0. So we have M minus 625 plus 125x equals 0. So M equals 625 minus 125x. Let's fill that in at some points along the length of x. So at x equals 0, M equals 625 kilonewton meters. At x equals 5 meters, M equals 625 minus 125 times 5, 0 kilonewton meters. So let's take a look at what those diagrams look like. So I have that worked out here for you. You can see that's all the calculations I just did. Here's the free body diagram. Here's the axial force diagram, where we have this column in compression, this beam in compression, and this column in tension. Here's our shear around the beam. And then look at this. Because these corners are moment connections, this moment has to transfer into this column. So it has to come out of this beam and transfer into this column. So these two values have to be the same. And we proved that that is the case. So the takeaway tips for today. If we know the forces, we can use the free body diagram to calculate the reactions. If we know the forces and the reactions, we can use the free body diagram of the part, remember that's method of sections, to calculate the internal force that must be there for the object to be static. We should know how to do method of sections on a beam. We should know how to do method of sections on a beam with no numbers. We should be able to draw a shear and bending moment diagram. Don't forget, you need your labels and your units. And we should be able to figure out the worst shear and moment from those diagrams or those calculations. Now, I have given you handy beam loading tables that will help you out with most of that. So I had some in this lecture. There is also in your downloads and in this module, beam loading tables for a lot of the common beam loading conditions that we'll see. So guys, or team, we now have one side of our equation. We know how to do it all. If these loads are factored, we now have the factored internal loads for everything we need to do. That means next week we can start looking at the other side of the equation, or what is the reduced capacity of these members. Okay, talk to you guys next week.